So our next section that we're going to be going over here is going to be displacement diagrams. And displacement diagrams are simply a graphical representation, and it plots the follower displacement relative to the driver. So when we talk about the follower, it's that end result, it's the output. It could be a nozzle like we saw in our last example where we're looking at the angle. But most often when we're looking at displacement diagrams, we're looking at linear displacement on something that would be a slider as the output. So like a piston in a cylinder would be a typical example of what we would use our displacement diagram for. So as we look at our displacement diagram, the x-axis, the horizontal axis, is going to be driver displacement in degrees. So it's going to be like our crank angle that we call it, okay? And then our y-axis is going to be the follower displacement in inches. So it's going to be the, how far did that slider go from its original position? So if we look at, I think I'm going to do this just a little bit different. Okay. So what we're going to do is we're going to go back to Canvas, and we're going to go to the learning plan for part 2 in module 1 here. And I've got two references. Okay. The two references that I have are a handout on inline slider crank. And we also have an Excel spreadsheet for an inline slider crank mechanism as well. If you guys had me for computer programming, we created this inline slider crank Excel spreadsheet for the results. So I have the one that I used and we created in class. But if you have yours from then, this would be the very same thing. So it was assignment 4 there. So don't worry about what the file says. But if you want to, go ahead and you can download that Excel file so that you have it available to you, because you will use it as a comparison. You will be handing in the result. But then the other one that I want to look at is going to be the PDF of the inline crank model. Okay. And I'm going to pull up first that PDF. And this kind of gives us a nice view of what's going on in this process. Again, if you had me for computer programming, this might look familiar as when we did this assignment in that class. So the inline slider crank mechanism, let's talk about inline. What inline means is that our crank is in line with the path of our slider. So you can see up here we have our slider. Might be a piston. It could be anything, that we're interested in. And then down here is our crank. So notice that when we have everything in line, the center line of the path of that slider is in line with the center of rotation for our crank. That's why it's called an inline slider crank mechanism. Now, in the position that we see here, you're going to notice that we call this 0 degrees. Okay. Or sometimes referred to as, in this case, if we're looking at in terms of a cylinder, this would be top dead center. This is also the limiting position of the furthest point that slider is away from the center of rotation of that crank. Do you see that? Okay. So it's kind of like identifying our limiting position as the starting point of our cycle, of our crank, rotation going around. So this is 0 degrees. Then you're going to notice that the next position that we have here is we're taking it and we are rotating our crank counterclockwise 45 degrees. So down here at link number 2, we rotated it 45 degrees from where it was originally at. Do you see that? In a counterclockwise direction. And what that did is it pulled our slider down a little bit. Okay. And notice that our measurement from the original position where everything was in line and it's top dead center, it now came down 0.377 inches. You guys see that? Okay. That's what we call the delta, or the displacement from that original position. Okay. And that's what happened when we changed our crank angle to be 45 degrees counterclockwise. Now we're going to move it another 45 degrees counterclockwise. So from the 0 position, we now went 90 degrees counterclockwise to our new position. And in that, we pulled the follower down even further. So now from its original top dead center, we are 1.172 down. Okay, then notice that we go another 45 degrees. Now we're another 1.792 down. And then lastly, we're in the 180 degree position. That's it's what we call bottom dead center, or the other limiting position. And now you're going to notice that we are 2 inches down from our original with this arrangement that we see here. Notice that each time we determined or we measured our displacement, our delta, it was always from that original top dead center, that 0 degree starting point. Okay. So any questions on kind of what we see here in terms of the action that's being taken, if you would? All right. Now what we want to do is we want to take these displacements and we want to plot them. We want to show a graph of what that looks like. So if we go back to the Module 1, Part 2 learning plan, we now have this Excel spreadsheet. So if you downloaded it already, if you didn't, go to your downloads, and we want to pull up that Excel spreadsheet. Okay. I'm going to put on enable editing. You can rename this if you want to, and I'm going to, it's my little thing here. I'm going to zoom out a little bit. So when you pull up that spreadsheet, what we have over on the right-hand side, this is a displacement diagram. Our x-axis is going to be crank angle. Our y-axis is going to be displacement. Displacement was the delta from that previous PDF that we just looked at. It was the distances that each time we would move our crank 45 degrees counterclockwise, it was that distance we kept measuring from that top dead center. Okay. So those are the values that we see here. Now, because it's an Excel spreadsheet, we programmed this so that our crank angle would be every 5 degrees. So that's why there's so many points along here. So as we look, here's 0, 50, 100, all the way to what would be 360 degrees, one full revolution of the crank in 5 degree increments. Then, depending on where we were at, so each time we moved at 5 degrees, if you would, kind of envisioning that last example that we looked at, we pulled that slider down just a little bit, right? And now we plotted that corresponding value. So this column right here, these deltas are the dimension from that top dead center. Those are those deltas that came down each time. So if I go back over here, oopsie, actually here, this delta dimension right there, I don't know why it does that. That delta dimension, 0.377, 1.172, and so on. Those are the delta dimensions that we see in that spreadsheet. Go back over here. They might not be for, is it the same? Hold on, I'm going to go back. Yeah, it's 1 and 3. So it's corresponding to exactly this handout, the numbers that we see there. So if we go to 45 degrees on the crank angle, we should see a delta of 0.377. So if I go back to Excel over here, here's my 45 degree line. My delta is 0.377. So if I go to 45 degrees here, that means that this point that's up would be 0.377 up. The course, I don't know exactly which one it is, but it would be corresponding. That's what we see as the plot points here. The X value, which would be the crank angle, and the Y value is going to be the delta, or the displacement from the original top dead center. Okay. So this gives us a graphical of what's going on as we rotate. Now, in an inline crank situation, our highest point, the difference between our highest point and the lowest point, is our stroke. Okay. So the stroke here, that this would have gone, the difference between the highest and that lowest point is going to be 2 inches. Okay. So notice that that's calculated over here, but we also see it graphically as the highest point on our graph. We should see this in an inline at the 180 degree mark, and we do. Okay, so notice that's a 2-inch dimension. Now, because it's in line, as we then start going on the other side of 180 degrees, our deltas are going to be a mirror image of what happened previous. So if we go to 175, notice that it was 1.977, but if we go to 185, 5 degrees past, it's that same value. So you can even see here, there would be a definite middle position at 180 degrees, and then it would be a mirror image on either side. Okay, does that make sense to everybody? So displacement diagram is a graphical representation of crank angle, okay, here, to the, in this case, piston or output displacement. Okay, now, knowing that, let's look at our book. We are going to look at example 411. Okay, example 411. They want us to draw, or they want us to create a displacement diagram for the piston arrangement we see right here. Okay, so actually this is a compressor, but it's a piston and a cylinder. We've got our crankshaft, which is going to be the first link here. We've got our connecting rod, and then we have our piston, which would be a slider that is constrained by the cylinder walls to only go in a linear fashion or have linear motion. So what we want to do, you're going to notice down here that this is the simplified kinematic diagram of the arrangement of the compressor example that we see above. So as you can imagine, what we want to do is we want to draw the kinematic diagram in AutoCAD and then check our mobility to be sure that our mobility equation comes out to 1, because the crank is the only thing that's doing the moving here. We should come out to 1. And then what we're going to do is we are going to strategically move it into some positions and check to be sure that our graphical solution comes out to the spreadsheet solution. Okay, so first things first, let's draw the kinematic diagram for this arrangement. You're going to notice that you have some dimensions up here, but if you wanted to look here, they added on them as well. So this is going to be example 411. I'm going to go to AutoCAD. I'm going to open up my kinematic start file, open, and then I'm going to draw this kinematic diagram to start off with. So I'll let you do that in the background as well. Oh, don't forget to rename. I do that sometimes. I'm going to do a save as. This is going to be example 411. Oops. Okay, so this is our compressor piston mechanism arrangement in the top dead center position, or what we would call 0 degrees. It's really what we're identifying as the start of determining, you know, the displacement diagram. So whenever we start a displacement diagram, if we need to create one, and you will be doing this for one of your assignment or for one of your assignment questions, I think it's number 70, the last one. You need to first create the kinematic diagram. And if it's not already in one of the extreme positions, you need to position it there. Okay. So notice that this is not, the crank isn't at some random angle around the 360 degrees. It's straight up, which would be its furthest extreme position. Okay. If it was straight down, that would be okay too. But right now it's in one of those extreme positions, which would be furthest up or furthest down. Okay, that's where we always start, one of the extreme positions. Once you've got it in an extreme position, now we're going to start maneuvering the crank. So at this point right here, even though this is technically, if you know, like standard 90 degrees, this is considered 0 degrees, the start position, 0 degrees on our displacement diagram. Okay, so if we go back to our Excel spreadsheet, if you would, the 0, 0, this is in its extreme position. Now, what I'm going to do is I'm going to update the lengths of my links here to reflect the example that we're doing. So the length of our link number 2. So you'll notice here, let me zoom in so that you kind of remember the inputs that we have to put in. We have to put in L2. This is the length of link number 2. Okay, link number 2, as I said, we're kind of like standardizing now. Number 1 is the frame, number 2 is the crank, 3 is the connecting rod, 4 is going to be your output. Okay, so link number 2's length in our example is 0.75. So I'm going to put in here 0.75. And then length number 3 is going to be the length of our connecting rod. In this example that we're looking at, for example, for 11, it's 2. You need to update the spreadsheet. You will be handing in the screenshot of this so that I can see that you updated it, because now we're going to use this where we're going to move our crank and we're going to compare to the values that we get to make sure that we're okay. All right. So now what this spreadsheet has done for us is it has created for us, oopsie, I'm going to zoom back out. It created for us not only, you know, the tabulated information here for all of the positions, but over here, why isn't, let me zoom out. There we go. I think it's just trying to catch up graphically. So it also creates for us the displacement diagram. Okay, automatically. It takes the tabulated information here and it puts it over here. So now what we're going to do is we are going to move this in a couple positions and make sure that our graphical solution, the dimensions that we get off of there, match what the Excel spreadsheet solution is. So we are going to move this. So right now it's in the 0 position. We already drew that. So we're going to go down here to, let's go to 45 degrees. That means that we're going to move our crank 45 degrees. Now, whether you move it clockwise or counterclockwise doesn't make a difference. I'm going to move mine counterclockwise because I strategically put all my labels on the right-hand side of that diagram so they wouldn't interfere as I move things around. So we're going to move the crank 45 degrees, and we're going to see how much displacement do we get from its original position at the top here to where now that slider comes down. We want to confirm that it's 0.291. So let's find out. If we draw correctly, it should come out that way. So we're going to go back to AutoCAD. Okay. So right now I'm going to label this line. I'm just going to kind of put this through here, and that's going to be the line. I have to move my number 4. That's going to be the line. That's going to be what I'm going to get my dimensions from each time. Move. No. Go here. And I might, actually, I'm going to extend that to be on the other side as well, because I think I might add my dimensions over on that side. Okay, so this is my original position. I want to move my crank counterclockwise 45 degrees. All right. So I am going to do a rotate on my crank. So I'm gonna say rotate. I'm gonna click on that crank, enter. I am going to identify my base position, which is the center of A. And then I am going to, before I hit my angle here, it's asking me for my angle already, but remember down here, we want to leave a copy behind. We want to leave the original copy down there or back there. And we want to then go 45 degrees and put in 45. If you don't hit the C or the copy at the bottom there, you'll just rotate that member as we identified before. I'm also going to change this line type to be object 2 so that we can see that difference. Okay. All right. Now I know that my slider is only going to be on a vertical line here. There's already link number 3 is there already. So that really is the path that that's going to take. So I'm not going to worry about creating another line. And all I'm going to do is I'm going to do a center radius from the end point of my crank. And now this is going to be the length of the connecting rod, which is 2. So the radius of that is going to be 2. So now what's going to happen is the intersection for that vertical line and the radius that I just created is going to be the new position of point C. It's going to be, if you would, the first C prime. Okay. Now, instead of moving the slider down, just because of the size of things here, I'm just going to move point C down. So I'm simply going to do a line. I'm going to go from the end point here to the intersection. Okay. And I am going to get rid of, I'm going to erase that radius there. And then I'm simply going to put my point designations here and here. Now, if we label each one of these, because we're going to move it another 45 and another 45. So we're going to do it in a couple different positions until we get to 180 degrees. And then we know that it's going to be a mirror image on the other side. So we're going to do it 3 more times. If I label each one of these C prime, C prime prime, it's going to be a mess. So all I want you to do is just show this new position. And then we are going to change to notes here. And we are going to add a linear dimension that is going to go from the center of my original to the center of the new position. Center here. There we go. That's my first dimension. I'm going to kind of put it out here. Okay. Now I moved this 45 degrees. If I look at my spreadsheet, what is the column that I should see 0.2913 in? Which column am I going to look at? The displacement, right? I just linear displaced this 0.291 when I move the crank 45 degrees. So if I go back to my Excel spreadsheet, here's 45 degrees, my crank angle. Right here in the displacement or the delta column 0.291, that's the corresponding amount. If I would kind of figure out which point this was, that means it would be 45 along here and it would be up 0.291. It's probably like this one here-ish, this one or this one. That's going to be the plot point that's on my Excel diagram. Does that make sense to everybody? So the X is the angle, 45 degrees, and the Y is going to be 0.291 up. Okay. And it looks, and I got that value. So that means that I constructed my first position here correctly. So I'm going to do a file save, and that's going to be my first one. Now I'm going to move it again, another 45 degrees. Now, if you wanted to change the color, good idea. I'm going to click on object 2. I'm going to add object 3. I'm going to leave it as a hidden line, but I'm going to change it to cyan and say, okay. Do that. I'm going to change this to object 3. And now I'm going to do that very same thing. I'm going to rotate. Now, whether you do link to the original or this one another 45 degrees, I'm going to do this one another 45 degrees. I selected it. I'm going to hit enter. My base position is going to be point A. And then I want to leave a copy behind. And then this is going to be 45 degrees. Remember, positive 45 is counterclockwise for polar. Oh, I should have done my endpoint too. So I'm going to just do that one right away. Okay. And then from that new point right there, I'm going to do a radius circle. And that is going to be the dimension of the connecting rod, which is 2 inches. So now down here is my new position for my point B, or I'm sorry, point C. Center to intersection. I'm going to change this to object 3. That's my new position. And then I'm just going to simply draw a line from the center here to the section. And then I can get rid of that construction radius. So my new position here, I'm going to maybe move this up and over. That's my first one. Now, and make sure you have at least 3 decimals so that you can check it to the spreadsheet, but 4 is good too. I'm going to leave mine at 4. Now my new distance is going to be, again, from the original to the new one. And this is my dimension. I'm going to change that to be on the proper line or the proper layer. Should be able to put it in between here. Oh, I didn't want to do that. Undo. You guys remember undo is your friend, right? Undo is up here. It's the backwards arrow. You can always undo actually till you started or opened that file. I'm going to do a quick save. So at the 90-degree mark, counterclockwise rotation of my crank, I pulled this down 90 degrees. My new position is 0.896. Let's look. If I go back to my spreadsheet and I go down to 90 degrees, sure enough, 0.896 is my delta value. So again, I would find where 90 degree is, 0.896. It's probably here-ish. Okay, that's the point. X and Y coordinates for that position. Any questions so far? All right. You don't need to reduplicate, like you don't have to draw these positions on here or figure what they're at. This is a check for you, but you will be handing in the screenshot for this Excel spreadsheet, matching the L2, the L3s, and then making sure that your deltas and your stroke are what they're supposed to be. So now I'm going to go back to AutoCAD, and guess what? We're going to move another 45 degrees, okay, counterclockwise. So I'm going to take my last one here. I'm going to do a rotate. And I'm going to grab that one. Oopsie. Rotate, select, enter. I just want that one. And I'm going to, my base position is going to be the center here. And I want to do a copy. So make sure you do C, enter, and then 45 degrees again, which would be 135 on our crank angle. And now we're going to, from that endpoint, now I need an object 4, it looks like. Oopsie. Object 4. I'm going to change this one to yellow. Okay. I'm going to put that on the object 4 again, so that I have object 4. So I have different colors here. I'm going to make object 4 my current layer. And then I'm going to do a circle radius. That radius is going to be 2 inches. And now the intersection on that vertical line is going to be my new position of my piston. Copy from here to here. And then I'm going to draw my line from here to there. And then I need my pin. I can get rid of the construction radius. And now I'm going to have a new dimension now down to the center of my piston. So I'm going to go to my notes, linear dimension from here to here. I have 1.32 probably, because I know I have 3 decimal places on my Excel spreadsheet. So I'm going to go down to the 135. Oh, 1.352. There it is. Okay, so I did get the same number. That means that I constructed it correctly. Right? And then we have one more to do, the 180. Okay, so we're going to rotate this 45 one more time. Do rotate on that. Center is going to be, oopsie, cancel. At the center here. I want to do a C for copy, and it's going to be another 45 degrees. So now we're going to be straight up and down. I need to add a layer. Looks like I need object 5. Oh, what color do I want it to be? I think I'm going to do magenta because that shows up pretty good. Even though I have my notes as magenta, that's okay. This is just another crank angle. I want to make sure that I can see the different colors. Okay. All right. And then if I put my radius on here, this is going to be 2. So my next position is right here. So Y, copy. And I'm going to go from here to here. And then I'm going to show this in its bottom position here, but it would be over the top of that very same line. So I just have to remember that that's my spot there. I'm going to take my joint, go from here to here, and I should get, let's see what we get for our dimension this time. So I'm going to change this to my notes, linear dimension from there to there to there. There's my center. Oh, exactly 1.5. Let's see. If we go back to our Excel spreadsheet and we go to 180. Oh, look at there, 1.5. And that actually happens to be, because this is an inline slider crank, that happens to be the very highest point on my curve, which is my stroke, 1.5. Okay. And then now from that highest point, which is the very middle of the inline slider crank, it's going to be a mirror image on the other side. Okay. So I would not draw any of the next ones because it's going to be exactly the very same values on the other side. Okay. It's a mirror image. So questions about displacement diagram. Number 1, you need to identify your limiting positions if you don't already have them, and you identify one of those limiting positions as the 0. If you don't, you get like curls on the ends of your diagram, and then you know it's not correct because it has to end and start at that 0 position. So notice that down here at the 0, 0, that's where everything starts. This represents that top dead center. These values are the displacements away from that top dead center, okay? So if you have these little curlies coming up on either side, that means you did not start at one of those limiting positions, okay? Because there's some extras on the ends. So if you have a wonky looking curve, that's probably the thing that you didn't do. So you identify your limiting position, you assign one of those as your crank 0. And then from there, you now are going to rotate your crank however many degrees, and then you're going to see what your follower does, in this case, the slider. And then you measure each time from the original position. Notice we didn't do distances between. We just kept going from that original 0 crank position. So all of these dimensions come from that top value down, top value down, top value down. Okay. All right, so I'm just going to do a very quick save on this. We're going to leave it there, and then we're going to go back to our PowerPoint presentation. Do I have that open somewhere? Maybe I don't. Maybe I closed it. So let me catch up. We're towards the end here. We're at the very tail end. So we did displacement diagram. We did example 411, which we just did. We created the plot. Now the plot is being created in Excel. You don't need to plot that, separately. And that is the very end of our PowerPoint. Okay. So now what we've done here in chapter 4, we've looked at really reinforcing kinematic diagrams, but we now have dimensions and we're drawing them to scale. We're then going to move those kinematic diagrams around and kind of see how the slave links or the links that are dependent on that crank are actually going to move in relationship to it. Then we looked at today the idea of limiting positions and determining, okay, what's the furthest and the nearest points? Okay, what's the extreme positions that those are going to move in, the output relative to our input or crank? And then once we know those limiting positions, identifying one of those and then creating a displacement diagram. Okay, that's the end. So we have gone through everything we needed to in chapter 4. So you're ready to work on the homework with what we've done here. Now, what I'm going to do is I'm going to stop our recording now and we're going to look at both the practice problems 1B and the assignment 1 part 2 so that you have a good idea of what you're going to be handing it. Okay, so I'm going to stop.